live here. We'll start tonight lesson, Skew-T soundings. Some of the team members seemed interested in learning more about the Skew-T soundings and how I use it for forecasting storms. So this is what we're going to do. We're going to go through that and then go through some graphs. Possibly we might turn this into a 2-session training depending on how the night goes.
I'm logged in.
Awesome, just in time, 103. Yep, I am recording it, so it will be available on YouTube, which would be a good thing because I think after you see this presentation, you'll want to get it where you can go back and review it. Now you also can take notes or take screenshots. If there's something you need a screenshot, if I got to go back, just let me know because there are information on a lot of these screens. So we'll get started here. Okay, Skew-T sounding, vertical profile of the atmosphere. I am going to go over the basics tonight to try to explain a little bit about it. At least I think after the presentation you can actually look at one and at least you know, try to figure out some of it, how to establish if the area is a very interesting area for storms or not. Yeah.
I guess it would have helped if I logged into Google first.
Yes, sir. All right, this will at least help you interpret some of the main features to help with pinpointing severe areas. There is a lot more information on a Skew-T sounding for the advanced meteorologist, so we're just going to try to cover the basics. All right, I'm using some visual aid here. We're going to be talking about positive buoyancy and negative buoyancy. So we got this visual aid here because we're going to be talking about air parcels rising with positive buoyancy, which if you think about a hot air balloon, that's what it does. And then we got did I mix my skew card sounding? All right, another visual aid. We talked about capped atmosphere. Just a visual aid for you here. Just picture the pot with the cover on it with boiling water. It can't rise. As soon as you take the top off, it rises. And this is, you know, just a visual aid just to think about what a capped atmosphere is. So we have to break the cap to get the air parcel to rise. What, I lost a note or something here.
And then this is a video right here.
All right, sorry about that. We had to check with the notes here. Okay, information from weather balloons and other sources are entered in a computer programs that generates the Skew-T sounding. It's all done by mathematical equation formulas. Like I said, I've looked at some of these. Excuse me, one sec. I looked at some of the formulas and they look pretty hard to, because I do not have a very high math background. It looked like it's possibly could be calculus. I think John was over last time and Four looked at it and she thought it looked like calculus. So a lot of this is all generated from mathematics after we send the weather balloon up and get all the readings. All right, I'm going to turn the video on here. It's about a 3-minute video, just to give you an idea how it's done. Everybody go ahead and press your arrow button and check out the video.
day-to-day operations. It is the only way we have to actually sample the atmosphere all the way up to about 100,000 feet. Well, here at the upper air building is where we actually go through the process of filling up the weather balloon. We use helium here at this office. Other offices also use hydrogen. And here on a standard day, we'll put about 1,200 grams of helium in. We launch rain or shine, hurricanes, blizzards, pouring down rain, anything except for lightning. If we hear any thunder within 15 minutes, we cannot launch the balloon. To repair the radiosonde, we take it out of the box, take a look at it, make sure all the sensors are working properly. We have a hygroscope that measures humidity, a temperature boom that measures temperature. Since all of this is GPS based, which you'll see up in the dome right there, we have to make sure that the radiosonde in the office is picking up the correct number of satellites. So we let it sit there for a few minutes to make sure it's catching all the satellites, make sure all the temperature data is correct. Once that is ready to go, we can bring the radiosonde down here and launch the balloon. We attach a parachute, so when the radiosonde does fall to the ground, it won't hit anybody, hit anything, cause any damage. After that, we will attach the parachute and the balloon to the radiosonde. After that, we launch the balloon. It gets to about 100,000 feet, takes 90 minutes to pop, and then we quality control and monitor the data for the next 90 minutes. These observations, after we take them, are carefully quality controlled by our staff, and then all of the observations go into our models to help us forecast. We also use the raw sounding data to actually help us with severe weather, rain snow lines when it comes to winter weather, and also helping us out with various other temperature and dew point predictions.
Okay, I hope everyone's done with the video and I will proceed. I hope that gave you a little bit of information of how this is done by the SBC. Jenny, what happened?
Alright, now we're going to remove the helium hose from the balloon. And since I just zip tied it in here,
I'm good.
Okay, and
That's
then
a pretty
go
good video.
right down there.
What the?
You go down here to the next slide. That little blue arrow.
Oh, there it is.
There you go.
Alright, sorry, had a little bit of difficulty there. Yeah, okay, we'll be moving on here. Alright, this is the observed sounding page for the SPC, which is the Storm Prediction Center. And these are called observed soundings. Remember that, there is a difference. This is an observed sounding, and the ones that we look at are called forecast soundings, which are done by the computer. So if you look here, you're going to see these are all the dates that, with all the information right here where they took soundings. Over here is an observed sounding from the SPC, which this is a Skew-T. This is similar to what we'll be looking at tonight. So, like I said, if you see an observed sounding, you know that is an actual sounding from a weather balloon. A forecasted sounding is computer-rated, generated by the computer. And if you look down here, look at all this. There's your National Weather Services that launched the balloons. Right there, that's Lincoln. I know I'm familiar with that. Davenport, but you notice there's none in for the Chicago. I'm sure that's because of the air traffic right here, I guess. I don't know, but there's some down in Mississippi. These are the launch sites for the balloons. Any questions so far?
Just out of curiosity, what would be the closest? I'm trying to look at the map there. It looks like Lincoln would be the closest balloon launch site for us.
That is true, and they're launched twice a day. You're gonna look at the sound road. I think it's like 7 in the morning and 7 in the evening right now. But twice a day they launch weather balloons, and sometimes they'll launch a special one during severe weather. They'll have to notify the FCC and everything, and they will launch one if there is severe weather in that area, a special occasion.
Receive, thank you.
All right, here's another little visual aid. You might just give you a few seconds to look at it. This is a diagram of the cloud structures. Check out that cumulus nimulus. This is what our thunderstorms look like compared to the other clouds. All right, we're gonna go, here's another quick video here. I wanted to refresh everybody. This is a good visual aid to show you what we're gonna be talking about tonight. So everybody go ahead and press the arrow, and I know you've seen it once, but this will help you, explain more about it tonight.
Hi everyone, Simon Keeling here, and in this Weather School video I want to show you a great example of growing cumulus and how that looks on a Skew-T diagram. So this was the cumulus cloud photographed over the west of Wales on one sunny or almost sunny Sunday morning. You can see the cumulus cloud there. Now I want you to notice how the cloud has formed. We've got the base here, look, and then we've got it growing gradually until it's achieved a top just in here. Now that level there is the top of the cloud, with this level here being the bottom of the cloud, and this line here shows us the total thickness of the cloud. Notice how the cloud base is dark. The sun was rising and shining here onto the cloud, so it did make that side of the cloud appear whiter and the bases appear darker. Now, the sky around the cloud is blue. It was quite an unstable air mass, which means that the lapse rate was quite sharp as you went upwards through the atmosphere. But this is how that would have appeared on a Skew-T diagram. So on the right-hand side we've got temperature, and on the left-hand side we've got dew point. So what happens here is that gradually, as the air mass rises within here to here, we've got air that's cooling off at 3 degrees Celsius per 1,000 feet, or at the dry adiabatic lapse rate. Now, once it reaches this level, then the air condenses out. It's reached a temperature at which the atmosphere can no longer hold the water as water vapour, and then it cools at the saturated adiabatic lapse rate for this distance in here. So it's now cooling at the saturated adiabatic lapse rate, which is around roughly 2 degrees Celsius per 1,000 feet. Then it reaches the point at the top of the cloud where all of the moisture has gone and the air then cools off again at the dry adiabatic lapse rate. So you see there how we get that whole depth of cloud within one single photograph. And that shape is easily visible on Skew-T diagrams. So there you have it, a quick Weather School video which I hope has proved useful for you. Now don't forget that you can see the very latest dates for courses held at Weather School by going to www.weatherschool.co.uk. We run one-day courses for aviators, sailors and also for farmers and just about anybody with an interest in the weather. We can do one-to-one tuition as well, and don't forget you can buy our DVDs and books online. We're all part of weatherweb.net. So, once again, thanks for watching and keep the sun shining. Bye for now.